The entire system, which stores, carries and controls the fuel supply for the engines, can be divided into two sections: the airframe fuel system and the engine fuel system. Here we'll look specifically at the engine fuel system, which receives the low-pressure fuel supply from the aircraft fuel tanks, which are part of the airframe fuel system. The engine fuel system increases the fuel pressure to a value that the fuel nozzles in the combustion chamber can use, and then controls the volume of fuel into the engine so that it conforms to the engine's requirements. The engine fuel system consists of a number of components which we'll now describe in more detail. The booster pumps, which are situated in the wing and centre tanks of the airframe fuel system, pass fuel through non-return valves to the engine via the low-pressure fuel cock. The low-pressure fuel cock is electrically operated. It can be shut automatically if the engine fire control handle is activated. If a component of the fuel system needs to be removed, for whatever purposes, the low-pressure fuel cock can be used to shut off the supply of fuel to the engine to facilitate the removal. If the high-pressure fuel cock cannot be used to shut down the engine for whatever reason, as an alternative, the low-pressure fuel cock can be used to stop the engine. However, using the low-pressure fuel cock to shut down the engine instead of the high-pressure fuel cock will mean that the engine will take much longer to shut down. This is because the pipeline between the low-pressure fuel cock and the engine contains a considerable amount of fuel, which will maintain the supply to the burners for some time, whereas in the case of the high-pressure fuel cock, very little fuel is contained in the pipeline between it and the combustion chambers. After it's passed through the low-pressure fuel cock, the fuel then enters the engine fuel system and is delivered to the low-pressure fuel pump. The low-pressure fuel pump is sometimes called the backing pump because it will attempt to back up the fuel supply to the engine in the event of failure of both of the booster pumps in the wing tanks. The low-pressure fuel pump is used to supply positive fuel pressure directly to the high-pressure pump. By maintaining a positive pressure, the low-pressure pump minimizes the chance of cavitation occurring at the inlet of the high-pressure pump. The low-pressure fuel pump is driven by the engine's accessory gearbox, which itself is driven by the high-pressure compressor shaft. A fuel-cooled oil cooler is fitted in the majority of gas turbine engine installations. The oil cooler serves the double purpose of cooling the oil and also heating the fuel. By raising the temperature of the fuel, the oil cooler eliminates the formation of ice crystals, which may block components downstream in the fuel system. The oil feed line to the fuel-cooled oil cooler incorporates a pressure-maintaining valve. This valve keeps the oil pressure in the cooler higher than the fuel pressure. If the oil cooler does develop an internal leak, then the fact that the oil pressure is higher than the fuel pressure will ensure that the oil leaks into the fuel system, rather than the fuel leaking into the oil system, which could be very dangerous. The fuel heater assists in the warming of the fuel, and thus the elimination of ice crystals. The fuel heater, working in conjunction with the fuel-cooled oil cooler, uses compressed bleed air to warm the fuel to automatically maintain a predetermined fuel temperature. The automatic temperature control can be achieved by the action of a Vernotherm thermal actuator. The thermal actuator incorporates a material which is sensitive to temperature change. This is used to open or close a valve, which regulates the entry of hot air into the fuel heater from the engine compressor. The low-pressure fuel filter is the first line of defense, protecting the delicate control components within the high-pressure fuel pump and the fuel control unit from the effects of dirt or contamination. The low-pressure filter is usually a replaceable paper filter element, which is capable of filtering out particles larger than 50 to 100 microns. The flow meter measures the instantaneous fuel flow in gallons per hour, kilograms per hour, or pounds per hour. The flow meter may also include an integrating system, which can add the total amount of fuel used. There are basically two types of flow meter in use on large jet aircraft. They are the vane type and the mass flow measuring type. The vane type of fuel flow meter, which is fitted to older aircraft systems, is designed to measure volume of flow. The flow meter consists of a vane which is moved against the force of a restraining spring by the volume of fuel flowing past it. This system is not too accurate. The mass flow type of instrument can be accurate to within plus or minus 1%. Fuel flowing through the instrument rotates both a drum and a spring-mounted impeller, which have magnets fixed to them. Movement of the magnets is sensed by pickup coils, which translate the difference in angular displacement between the magnets into a mass flow rate. The fuel temperature is sensed as the fuel leaves the fuel heater. Fuel temperature is indicated on the flight deck to allow system monitoring. The fuel pressure is sensed as the fuel leaves the low-pressure fuel filter. Fuel low pressure may be indicated by either an LP fuel warning light or the activation of warnings on the ICAS or ECAM, depending on aircraft type. The high-pressure fuel pump is fitted to and driven by the engine accessory gearbox. The engine accessory gearbox itself is driven by the high-pressure compressor shaft. The high-pressure fuel pump, illustrated, is representative of one type of pump employed. It's a plunger-type pump. It can be used as a single unit, if the volume of fuel required is not too great, but in larger engines, two units can be driven together to supply a greater fuel flow. Several plungers are fitted on a rotor assembly. The plungers are rotated against a stationary cam plate, which causes them to reciprocate within the bores that contain them on the rotor assembly. The distance that the plungers move during this reciprocating action is dictated by the angle of inclination of the cam plate. Here we see the cam plate angled so that the plungers stay in the same position in their bores as the rotor drives them round. Now the cam plate angle is such that the springs force the plungers to their maximum stroke when they are at the top of the cam plate, sucking fuel into the bores. And the cam plate forces the plungers to their minimum stroke when they are at the bottom of the cam plate, forcing fuel under pressure to the outlet of the pump. The angle of inclination of the cam plate is controlled by a servo piston, which itself is controlled from the fuel control unit. Most fuel systems incorporate a fuel filter into the output of the high-pressure fuel pump to prevent very fine particles entering the extremely small passageways inside the fuel control unit. The fuel filter is composed of a number of wire mesh screen discs. The spur gear type fuel pump is simpler and lighter in construction than the plunger type fuel pump, and like the plunger type pump, the spur gear type pump is driven by the accessory gearbox. The output of the spur gear type pump is directly proportional to its rotational speed. The fuel control unit controls the fuel flow to the burners for every thrust setting. There are two types of hydromechanical fuel control systems still used on gas turbine engines. They are the pressure control system and the proportional flow control system. The proportional flow control system is the more popular of the two types because it is more compact than the pressure control system, and it's not sensitive to the effect of flow variations that occur downstream of the throttle. The proportional flow control system is the type we'll use to describe the individual parts of a fuel control unit. Various devices within the fuel control unit are used to adjust the fuel flow to cater for variations in air intake pressure, engine acceleration control, exhaust gas temperature, RPM limiting, and compressor